Okay, so we talk about heap sort. So before that we talk about what is heap. So heap is a data structure which is basically an array, but it is viewed as a nearly complete binary tree array, but it is viewed as a binary tree. Okay. So it is basically an array. So suppose let us take an array. Say we have an array like this 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. Suppose this is an array, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, there are 10 elements. So, how we can view this array as a binary tree? So, we just take the first node A1 as a root, A1 as a root of the tree. Okay. Then we take its left child and right child as A2, A3, and then A4, A5, A6, A7, A8, A9. There are 10 elements. So, A10. Okay. So, we are viewing this binary tree. So, A1 is 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. So, this array any array we can view it like this as a tree. So, that means, if we have AI over here, if this is AI. So, for AI what is the left child of AI? It is basically A 2i and A 2i plus 1 is the right child of AI. And what is the parent of AI? Is basically AI by 2, I mean ceiling, integer part of this. So, basically the parent of I is basically I by 2, and the left child of I is basically A 2i, and the right child of I is basically A 2i plus 1. So, this is the this is the position of the left and right child of AI, and this is the position of the parent. So, any array we can view it as a binary tree. This is nearly complete binary tree, because if number of element, if n is 2 to the power 2 to the in a power of 2, then we have a complete tree. Here it is 10. So, if there are 11, 12, 13, 14, if there are 15 elements, then we have a complete tree. So, that is why it is called nearly complete binary tree. So, what is the height of this tree? Height is basically log n. That is why it is nearly. So, it is a good tree, but the advantage of this tree is we are viewing this tree. I mean, we are not, I mean, we do not need any pointer to implement this tree. Usually for tree implementation, you need a pointer for the left sub array, right sub array, parent, but here we do not need that. We do not need, no pointer is required to have this tree. Because if we know the I mean we know if I is 4, then we know the childs are basically 2i plus 1. So, this tree is just we are viewing like this. So, we do not need to have any pointer to implement this tree. Okay, so this is called heap. This data structure, this array is called heap, which is viewed as a tree like this. So, this is called heap. Okay. Now, we introduce a Maxif which is a property in this heap. So, if every element is greater than from its child. So, if the key value of every element, so that means, so here it is a I and we have the child a to I, a to I plus 1. So, if a I is greater than maximum of these two, a to I, a to I plus 1. That means, if the every node is greater than from its child, the key value of the node is greater than from its child, then it is called a, and if this is true for all I, if this is true for all I, then we call our heap is a Maxif. Then the heap is a Maxif, or we can say our heap is having a Maxif property. Okay. And similarly, we can define the mean heap. So, if any node is less than, from value of that node is less than its child, and this is true for all node, then we call that heap as a mean heap. So, we will talk about max heap and we will see how we can use this to have a sorting algorithm. So, this heap is nothing to do with sorting, I mean heap we can study independently. So, this is basically a data structure, this is used for the priority queue implementation. So, and so now we will talk about how we can have a Maxif array from a given array. So, is this array is a Maxif array in this example? So, this array is basically 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. So, this is our given array, and the question is this a Maxif array? So, you have to check whether each node is greater than from its child. So, 16 is greater than from its child, 14 is greater than 8 and 7, 8 is greater than this, 7 is greater than this, 10 is greater, yeah. So, this is a Maxif array, this array is a Maxif. So, it is preserving the property that each node is bigger than from its child. Now, but if we have some array which is not Maxif array, now the question is how we can make that array as a Maxif array. So, the input is any array, an unordered array, and we want to make it, output will be, our goal is to make it Maxif array. Okay. So, this we want to discuss how we can do that. So, for this we need two subroutine, one is called build Maxif, so this is the algo for this. So, it will take an array and it will convert into Maxif array, and in the build Maxif we will use a subroutine which is called max heapify. A comma I. Suppose we have a, this is our AI and this is 2I, I mean this is 2I plus 1, that is that means the left sub array, and this is the right sub array of AI. Now we are calling this maxify of this array at the point A. So for this pseudo code or for this code we need to have an assumption. That assumption is, so we assume this left sub array is already maxify, right sub array is already maxify. So we have to handle this here. So here we have a violation of the maxify. So this code can handle only one violation. So everything is okay here, everything is okay here, only we may have a violation at this level. So that is how we can handle this. Is this clear? So this code can handle only under this assumption that the left sub array of I is maxify, right sub array of I is maxify, only we may have a problem over here. So that we have to handle. So that is our that is by the maxify code. So let us see what is the maxify, how it is working. Okay, we will take an example by which we will suppose we have this array 4, 10, 14, 7, 9, 3, 2, 8, 1. So this is an array like this 16, 4, 10, 14, 7, 9, 3, 2, 8, 1. So this is our input given array. Okay. Now this is 1, 2, 3, 4, 5, 6, these are the indices 7, 8, 9, 10. Now if we look at this node, so if you look at this node, this is our I, say I is equal to 2. This node we have a problem. What is the problem? Because this node is not greater than from its child, it is less than even both of the child. So it is not a Maxif property is violating here. But if you look at the left sub array and if we look at the right sub array of this ith node, this is Maxif array, this is Maxif. So no violation in these two, only violation we have here. So that is can be handled by this code. So what we call here, we call the maxify at the point I is equal to 2. This is the, so we have a violation here, but for that we need to have everything is okay here, everything is okay here, that is there. Okay. So now how we can handle this, violation. So we check these two, whichever is the maximum we replace that with this. So 14 is the maximum, so what we do, we replace 14 by 4. So 14 will go here and 4 will come here. Okay. So now this is basically 4. Now once 4 will come here, then we may need to check whether this is violating the maxify property here or not. This problem will come down. So now here also it is not, but it is not maxify. So what we need to call? We need to call again the maxify a comma I is equal to 4. So then if we call this, when we calling, then we are make sure that these two part is maxify. This is only one element, so it is maxify. This is the lib node. So now what we do, we exchange this with the maximum of these two. So maximum is 8, So, we exchange 8 and 4, and then this is there is no further, this is the lib node. So, we stop here. So, this is the Maxify code, I mean the execution of the Maxify. So, what is the time complexity for this? So, time is basically log n, because if our height of the tree is n, we may have to start from the root. Okay. So, it is basically log n, height of the tree. So, every time we are exchanging the maximum value and we are just calling the Maxify again. Now, again you have to call the Maxify here at a comma, this is 9, but this is a lib node, it is already Maxify. So, you stop here. So, this is the Maxify subroutine, but this can handle only if two parties, the left part of the array is Maxif and right part of the array is Maxif property, only we can handle one violation. Okay. So, now how we can use this to build a Maxif array? So, that we will now discuss. Okay. So, next we will talk about build Maxif. So, it is taken an array A of size n. Okay, it is very simple code, 2-line code. This is the simplest code I ever seen. So, this is for I n by 2 down to 1. We call the Maxify. A comma I, that is it. So, this is the pseudo code for build Maxif. Now, the question is why you are starting from n by 2 to 1, why not? So, this is our array is from 1 to n. So, the question is n by 2, then n by 2 plus 1 to n. Question is we are not looking at this elements, we are just calling this Maxify only from n by 2. So, what is the reason for that? Because see, look at this array. So, this is a 1, 2, 3 like this. This is our, anyway maybe we have up to this. Okay. So, this is 1, 2, 3, 4, 5, 6. So, can you tell me what is this element basically? N by 2 to n by a n by 2 plus 1 to n. These are all basically lib nodes, because if we take any nodes from, if we take any index from here, then 2i to I plus is out of the range. If we, so these are all lib nodes, these are all libs. So, libs is already Maxify, we have only one node, it is already Maxify. So, you do not need to care about the libs, but these are the nodes. So, these are all from n by 2 to n. Now, only thing, now this is the node at a, this is a n by 2, this is n by 2, this is the first node which is having at least one child. Okay. Now, we need to do care from this, because this may be having some violation of Maxif. So, we need to call the Maxif here. Now, when we are calling, we are ensuring that this is Maxif, because it has only, if we have two child also, there are only lib nodes. So, they are already Maxif. So, we need to call Maxif only this, like this way we will continue and we will reach to the root. So, this is the code for this. Okay. So, what is the time complexity for this? What is the time for this code? Intuitively, it's maybe you are thinking that it is n log n, because there are n nodes and each in the it maybe the log n is the height, but you see here not for all nodes we are spending log n time, because these are the nodes which is just having one comparison, because for this node we are just comparing one time Maxif call, comparing this maximum and that is it. So, for this first level node we are just comparing 1. So, how many such nodes are there which is on this level? I mean we can say this is from here it is level 1. So, there are n by 4 node. So, there are n by 4 node which is are this level. So, how many comparison we are doing for this? We are doing constant comparison. So, n by 4 into 1 into C, and in the next level when we are calling the Maxify again. So, for them we may need to go down twice. Okay. So, how many such nodes are there? N by 8 into 2C, the constant comparison we may say. So, then like this n by 16 into 3C like this dot dot dot, but at the root level root has to come down. For the root level when you are calling the Maxify it has to come log n time. So, this is the exact time for this code. Now, if you take n by 4 is equal to 2 to the power k, then this is coming out to be C into 2 to the power k 1 by 2 to the power 0 plus 2 by 2 to the power 1 plus 3 by 2 square plus dot 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 k plus 1 by 2 to the power k. Okay. Now, this term is basically a constant. So, this constant can be plugged with this, and this is basically a order of big O of n. Okay. So, this is the linear time algorithm. So, time complexity is this is big O of n. Okay. So, now we will so this is the build Maxif. So, we have given a array, any unordered array, how we can make it a Maxif array. So, now we will see how we can use this Maxif array to have a sorting algorithm. So far we have not talked about this. We start the heap which is nothing to do with sorting, but we now will see how we can use this to have a sorting algorithm, and that is called heap sort. Okay. So, we have a array, we need to, this is a sorting problem. So, we have a array of size n and we need to sort it. So, what we do? We define the size of the array, this is as n. So, now we call the build Maxif on this array. So, once we call the build Maxif on this array, so it will give us a Maxif array where maximum is belonging to A1. So, like this. Okay, like this. Okay. So, maybe we have some more element. This what is the n? Now, what we do? We just exchange this A1 and AN. We just exchange A1 with the last element, and we reduce the size of the array by 1. Okay. That means, the last element is in its position. Now, again we, so when we are swapping, So, everything was fine here. So, now this was a new element. So, this may get violation of the Maxify. So, then but for there we know this is okay, this is okay. So, now we need to call Maxify at this level. Okay. And then after calling the Maxify, we will go to, sorry, this is 5, this is 6. We will go to step 3, and we continue this until the size become 1. So, this is the code. So, we can take a quick example how this is working. Okay, so, this was our array. So, 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. So, we can just draw the, so anyway this is a Maxif array, 14, 10, 8, 7, 9, 3, 2, 4, 1. Okay. So, we may have a general array, but we can make it a Maxif array. So, suppose we have an array, so we made it Maxif array. So, we got this. So, after this step we have this. Now, what we do? Our size here is 10. So, what we do? We exchange this is the A10 and this is the 1. We exchange this with this. So, 16 will be coming here, 16 and 1 will be going here. So, this is now 1. Okay. Now, we discard this link. So, 16 is in correct position, we discussed this. So, this tree we are viewing, this tree does not exist, we are not implementing this tree, everything is we are doing in this array. So, that is why it is called in place sort. We do not need to have extra memory or something, everything we are doing here. So, this is now 1. So, now this may violate the Maxif property. So, we again do the Maxify for this. So, this will exchange with this. So, 1 will come here. So, this 1 will come here, 8 will go here. So, this 1 will come here, 4 will go there. So, then we will reduce the size. Now, the size is 9. So, now this is our so now this 14 we exchange with this 1 again. So, this is 14 now. So, this is 1 again. So, this 14 we cut this link and we reduce the size. So, this way we continue and at the end we got the sorted array. So, we just forget this part because this is already in its position. So, like this we can. So, what is the time complexity? So, this will linear time, and here we have a for loop. This is on the size of the array n, and each time we are calling the Maxify, this may take log n, because up to n by 2 it is taking log n. After that we have, so this will take n log n. So, in total time is theta of n log n. So, this is same time complexity as merge sort, but this is better in the sense this is a in place sort. So, we are not using any extra memory for this, everything we are doing in an array, only thing we are viewing this array as a tree, we are not implementing this tree is just our view. So, everything we are doing in the array itself. So, this is in place, but for the merge sort we need to have the extra array for that merge subroutine in a linear time. Okay. Thank you.